Category O, lecture number 1, preliminaries and definitions. So we start with a brief description of the literature which can be used for basics of Lie algebra structures. One of the best books for basic Lie algebra theory is the book by Serre, which is called Lie algebras and Lie groups from 1964. A more recent book is a book by Erdmann and Wilden, Introduction to Lie algebras, which is from 2006. It contains a lot of details and also a slightly different approach to the one which you can find in the literature for several statements. The standard book for basic Lie algebra course is Humphreys, Introduction to Lie algebras and Representation Theory. However, it is quite densely written and might be a tough read for an unprepared student. So the book of Erdmann and Wilden gives much more details. The following YouTube channel will contain a list of lectures on basic Lie algebras. In relation to category O, the oldest book which treats structure of highest weight modules, in particular of Verma modules, is Dixmier enveloping algebras. Furthermore, a very good read is Janssen's book on enveloping algebras. It has a disadvantage that it is in German. The general theory of category O for the abstract setup of Lie algebras with triangular decomposition can be found in the book of Moody and Pianzola. There is also a fairly recent book of Humphreys, which is purely dedicated to the questions related to category O over semi-simple finite dimensional Lie algebras. So it gives a very good amount of details for everything up to the Kazhdan-Lusztig conjecture. A number of more advanced topics are covered by my lecture notes on algebraic categorification. However, this doesn't have any serious proofs. On the other hand, my lectures on SL2 modules have very detailed treatment of category O for the very particular smallest case of the Lie algebra SL2. So let's start with a setup. So let G denote the semi-simple finite dimensional complex Lie algebra. The general notation for a Lie algebra A we will denote by U of A, the universal enveloping algebra of A, and by Z of A, the center of U of A. Let us fix a Cartan subalgebra of G. Recall that a Cartan subalgebra of a semi-simple finite dimensional Lie algebra is abelian. Moreover, all Cartan subalgebras belong to the same orbit of the action of the group of inner automorphisms of G. So up to some natural notion of equivalence, it doesn't matter which Cartan subalgebra we fix. Associated to this Cartan subalgebra, we have the root space decomposition of G as a direct sum of the Cartan subalgebra and the corresponding root spaces. So the roots are elements in the dual subspace to the Cartan, and for each root alpha, the corresponding root subspace consists of all elements in our Lie algebra G, which are eigenvectors to the adjoint operator of H, with eigenvalue alpha of H, where H is an arbitrary element of our Cartan subalgebra. So root subspaces are common eigenvectors for all Cartan elements, with the eigenvalues prescribed by the root. So in particular, we have the root system phi of G, so this is a finite subset of the dual space to the Cartan, and associated to it we have its Weil group W. Furthermore, if we fix a basis pi in our root system phi, then the root system decomposes into a disjoint union of positive and negative roots. So the set of positive roots phi plus is the set of all roots which have non-negative integral coefficients when written as linear combinations of elements in the basis. And the set of all negative roots, these are the roots which have non-positive integral coefficients when written as linear combinations of elements in the basis. By adding up all root subspaces corresponding to positive, respectively negative roots, we get the positive, respectively negative nilpotent subalgebras n plus and n minus. The direct sum of the Cartan subalgebra H and the positive nilpotent subalgebra n plus is called the Borel subalgebra and usually denoted by B. So we have a decomposition of G into a direct sum of three subalgebras, n minus, h, and n plus. However, this is a decomposition only as a vector space. So this is not a decomposition into a direct sum of Lie subalgebras. So the elements of h and n plus, they do not commute in general. Also, an important piece of this triangular decomposition is the Chevalier anti-involution sigma, which is a certain anti-involution on the Lie algebra G, which swaps n plus and n minus and acts as the identity on the Cartan subalgebra H. Let's consider one very abstract example of SLN. So the Lie algebra SLN is a Lie algebra of all n times n complex matrices of trace 0. The standard Cartan subalgebra of SLN consists of all diagonal matrices. Then n plus is the subalgebra of all upper triangular matrices. N minus is the subalgebra, this should be n minus, the subalgebra of all strictly lower triangular matrices. And in order to describe the root system, let us identify H as a subspace of the vector space Cn consisting of all vectors whose coordinates add up to 0. Obviously, such vectors are in bijection with diagonal matrices, so we just write d1, d2, and so on, dn on the diagonal, and then the condition that the sum of the diagonal entries is equal to 0 exactly corresponds to the conditions that the trace of our matrix should be 0. So H can be identified with the codimension 1 subspace of Cn. So we have the standard basis of Cn consisting of E1, E2, and so on, En. And this gives us the dual basis epsilon of Cn star, which consists of the functionals epsilon 1 and so on, epsilon n, defined such that the evaluation of epsilon I at the basis element Ej is equal to delta Ij. So now we have identified H as a subspace of Cn. Then H star can be naturally identified with the quotient of Cn star by the subspace given by the sum as a linear span of the sum of all elements in the standard dual basis of Cn star. So the root system of our Lie algebra SLN in this notation is given by the roots epsilon I minus epsilon j, where I and j are different elements from 1 to n. The positive roots correspond to roots where I is less than j, and the negative roots correspond to roots where I is greater than j. And the natural basis is given by epsilon I minus epsilon I plus 1, where I is from 1 to n minus 1. So if we denote by Eij the usual matrix units, which is a matrix where you have the entry in the i's row and j's column equal to 1 and the rest is 0, then we have the following natural description of root subspaces. The root subspace for SLN for the root epsilon I minus epsilon j is a linear span of Eij if I is less than j, and is a linear span of EJI if I is bigger than J. So this distinguishes positive and negative roots. And the Chevalier anti-involution on SLN is just the usual transposition. The Weyl group of SLN is the symmetric group Sn, which acts naturally on Cn dual by permuting the elements of the standard basis, and this induces the action on the quotient because the sum of the basis element is invariant under this action. A very concrete example is the Lie algebra SL2. So this is the algebra of all traceless 2 times 2 matrices. It has dimension 3 with a standard basis given by the matrix F, where we have 1 below the diagonal and the rest is 0. We have the diagonal matrix H with 1 and minus 1 on the diagonal. It must have trace 0. And the upper triangular matrix E, which has 1 above the diagonal and the rest is 0. So this is a 3-dimensional Lie algebra, and since the Lie bracket is anti-commutative, so the Lie bracket is explicitly given by 3 values, and these are easy to compute. The commutator of E and F is equal to H, the commutator of H and E is equal to 2E, and the commutator of H and F is equal to minus 2F. So in particular, E is an eigenvector for H with eigenvalue 2, and F is an eigenvector for bracketing with H with eigenvalue minus 2. So the Cartan subalgebra is spanned by H, the positive nilpotent subalgebra is spanned by E, and the negative nilpotent subalgebra is spanned by F. The root system consists of 2 roots, plus and minus alpha, where the evaluation of alpha at H is equal to 2, and alpha gives the natural basis of this root system. So now we are ready to define category O. So to define category O, we fix a semi-simple finite-dimensional complex Lie algebra and a triangular decomposition G is equal to n minus plus H plus n plus of this Lie algebra. Category O was defined by Joseph Bernstein, Israel Gelfand, and Sergei Gelfand, 1976. So the category O associated to this triangular decomposition of G is defined as a full subcategory of the category of G modules, which consists of all G modules that are finitely generated, h-diagonalizable, and locally un plus finite. In a moment, we will discuss in details all these 3 conditions. First, 2 remarks. The notation, so the letter O is the first letter of the Russian word основная, which means in English main or principal. So this is most probably the origin of the notation. And the reference for the definition of this category is a paper by Bernstein, Gelfand, and Gelfand, which is called A Certain Category of G Modules, published in Functional Analysis and Its Applications in 1976. So the first condition, that the modules in category O are supposed to be finitely generated. The condition to be finitely generated is an algebraic equivalence of compactness. Indeed, if you have a finitely generated module, then any cover of this module has a finite subcover because it is enough to cover the generators, and there are finitely many of them. One can remark that the universal enveloping algebra of G is a non-commutative Noetherian algebra. So the reason for that is that it's a filtered algebra with a filtration by degree of monomials given by the Poincaré-Berghoff-Witz theorem, and the associated graded algebra, it's a polynomial algebra in finitely many variables and hence Noetherian. So this implies that U of G is Noetherian, and for Noetherian algebras, finitely generated modules form a very natural subcategory to study. In particular, it follows that category O is closed under taking submodules. So we will discuss this in more details slightly later. So this is about the first condition of being finitely generated. The second condition, that modules in category O are supposed to be h-diagonalizable. Observe that H, the Cartan subalgebra of a finite dimensional semi-simple Lie algebra, is commutative. Hence, all simple H modules are one-dimensional and are given by linear functionals on H. If we fix such a linear functional gamma, then the corresponding module L gamma is a one-dimensional complex vector space C with a standard basis given by the element 1, and the action of H is given as follows. If we have an element H in H, then H applied to 1 gives us a scalar multiple of 1 with a scalar given by gamma evaluated at H. So L gamma, where gamma is an element in H star, exhausts all simple H modules. So this allows us, for any linear functional lambda on H and any G module M, to define a subspace lambda inside M as a set of all vectors M inside M, such that the action of H on such a vector is given by lambda of H times this vector. In other words, this is the isotypic component of the restriction of M to H, which corresponds to the simple module L lambda. The usual terminology in this setup is that elements lambda in H star are called weights, and this subspace M lambda is called the weight subspace or the weight space corresponding to weight lambda. And elements in M lambda are called weight elements or weight vectors. A module M is called a weight module, provided that it is a direct sum of its weight spaces. For example, the adjoint module is a weight module because the root space decomposition is exactly the decomposition of the adjoint module into its weight spaces. On the other hand, the left regular representation of the universal enveloping algebra is not a weight module because the action of the universal enveloping algebra of the Cartan subalgebra on U of G is free. So there are no eigenvectors at all. And for a weight module M, the support of M is defined as a set of all weights such that the corresponding weight space is non-zero. So this is just a reformulation that weight modules are exactly the modules on which the action of the Cartan subalgebra is diagonalizable or semi-simple. Before we go to the discussion of the third condition, local UN plus finiteness, we make two detours. First, let's talk about the Schur-Dixmier Lemma. Each element of the center of the universal enveloping algebra acts as a scalar on any simple G module. But the big difference with the usual Schur's lemma is that we do not assume that the module in question, the simple module in question, is finite dimensional. Proof. Assume that L is a simple G module, not necessarily finite dimensional, and Z is a non-zero element of the center. So if Z is a zero element of the center, there is nothing to talk about. Case number one, if Z has a non-zero eigenvector in this module corresponding to eigenvalue to some eigenvalue chi, then the corresponding eigenspace, so the set of all eigenvectors for Z with eigenvalue chi, is by the usual linear algebra a submodule of L. This is because Z commutes with the action of U of G. And therefore, by simplicity of L, this must coincide with L, which means that Z acts on L as chi, as the scalar chi. So the opposite case is the case where Z doesn't have any non-zero eigenvector. In particular, any non-zero polynomial in Z doesn't have any non-zero eigenvector. This is because if a polynomial has an eigenvector, we work over an algebraically closed field, so we can factor this polynomial into linear factors, and then one of these linear factors must have an eigenvector, and we are in case 1. So the opposite of case 1 is when any non-zero polynomial in Z acts injectively on our module. Of course, since Z is central, the image, any polynomial in Z is central, and the image of such polynomial also should be a submodule of L, and hence must coincide with L due to simplicity of L. Therefore, this action is even bijective. But then this implies that we can invert the action, and we get that our module L is a module over the field of rational functions in Z. However, the field of rational functions in Z has uncountable dimension over the complex numbers. This is simply because the rational functions 1 divided by Z minus lambda, where lambda is a complex number, are linearly independent, and the set of complex numbers is uncountable. At the same time, each simple G module must have countable dimension because it is a quotient of the universal enveloping algebra, which has countable dimension over C. So this contradiction proves our theorem. So detour number 2 is Bernstein's inequality. Consider the polynomial algebra lambda in n variables. The Weil algebra AN is the subalgebra of the algebra of all linear endomorphisms of lambda, generated by the multiplication with each variable xi and the partial derivative with respect to each variable xi. In 1972, Bernstein proved the following theorem: that the Gelfand-Kirillov dimension of any simple AN module is at least n. So here, the Gelfand-Kirillov dimension is the measure how finitely generated modules over finitely generated algebras grow. So we start with a finitely generated algebra and with a natural filtration of this algebra by degrees of monomials in products of generators. And then, given any finitely generated module, we can associate to this module the filtration by subspaces given by applying the filtration of the algebra to the generators. And then we can look at the growth of the corresponding sequence of dimensions. So if the growth is polynomial, then the degree of that polynomial is called the Gelfand-Kirillov dimension of the module. And so Bernstein proved that the Gelfand-Kirillov dimension of any simple AN module is at least n. At the same time, the Gelfand-Kirillov dimension of the regular module, so the Gelfand-Kirillov dimension of the algebra AN, is 2n. So this inequality says that the Gelfand-Kirillov dimension of any simple module is at least 1/2 of the Gelfand-Kirillov dimension of the algebra. So modules of minimal possible Gelfand-Kirillov dimension are called holonomic and forms in some sense the simplest class of modules. Non-holonomic modules are very difficult to construct and very difficult to study. So for example, for Weil algebras, there is some kind of classification of simple A1 modules, and there is a similar kind of classification of simple holonomic A2 modules. To make a parallel with a finite dimensional intuition, the simple algebra of n times n complex matrices has dimension n squared, while its simple module Cn has dimension n. Gelfand-Kirillov dimension is logarithmic in nature. It describes the degree of the polynomial. So if we take the logarithmic version, then we have that the logarithm of the dimension of the algebra here is 2, basically, and the logarithm of the dimension of the module, the degree is 1. So the dimension of the simple module is logarithmically 1/2 of the dimension of the algebra. This is very rough speculation, of course, because we cannot apply the Gelfand-Kirillov dimension of finite dimensional structures is, of course, 0 because they do not grow. But in some sense, one can see that the logarithm here, so the degree here is twice bigger than the degree of the simple module. And the Bernstein inequality is in some sense the infinite dimensional analog of this observation. Note that the Bernstein inequality is really an inequality. It says that the Gelfand-Kirillov dimension is at least n, but it can be bigger. And there are, in some sense, almost all simple modules over a simple algebra are not holonomic, usually. So with these two detours in mind, let's discuss the third condition, the condition of locally finite action of the universal enveloping algebra of the positive part. So somehow Bernstein's inequality suggests that in order to get a reasonable category of modules over a simple algebra, one needs to kill 1/2 of the available parameters. So if the algebra is generated by 2k elements, it will probably have the Gelfand-Kirillov dimension 2k, and the module, the simple module, minimal possible Gelfand-Kirillov dimension should be k. So we need to kill 1/2 of the parameters. Of course, the algebra U of G is not simple because it has a center, which has roughly the same size as the universal enveloping algebra of the Cartan subalgebra. Here, one can speculate that the condition of h-diagonalizability, so the second condition in the definition of category O, it compensates for the non-simplicity of UG with respect to the center. So simple modules should have central character, so the condition of h-diagonalizability somehow guarantees that category O will contain simple module, which automatically will have central character, and thus takes out the parameters which corresponds to the Cartan subalgebra. So since our algebra G has a triangular decomposition n minus plus h plus n plus, and this condition takes h out of the game, what remains is n minus and n plus. So we can intuitively speculate that the condition that the action of un plus should be locally finite, it kills the parameters, 1/2 of the remaining parameters which correspond to n plus. Basically, it prescribes that the elements of n plus act locally nilpotently and hence have only one eigenvalue, namely 0. So this is some kind of rough intuitive description why we need these kinds of conditions. So let's discuss some basic properties of category O. As we have already mentioned, the category O is stable under taking submodules. So here, finite generation, that this is stable under taking submodules, uses Noetherianity of our algebra, while h-diagonalizability and locally un plus finiteness, these two conditions are obviously inherited by submodules. The dual property is that O is stable under taking quotients. Here, all conditions obviously follow. So quotients of finitely generated modules are finitely generated. Quotients of h-diagonalizable modules are h-diagonalizable. And quotients of modules on which un plus acts locally finitely are modules on which un plus acts locally finitely. So the next property is that category O is obviously stable under taking finite direct sums. The consequence of this is that category O is actually an abelian subcategory of the category of all G modules. So the abelian structure of the category of all G modules is inherited by category O. So this is an abelian category. Still, it is quite a big category, as we will see in the next lecture, when we will show that it contains continuum many simple objects. One nice observation is that category O contains the category of finite dimensional G modules. This is not totally obvious. It is very easy to show, we will discuss it in the next lecture, that all simple finite dimensional modules belong to category O. So that they are finitely generated is obvious, and that the sum action is locally finite is also obvious. So what is not obvious is that simple finite dimensional modules are h-diagonalizable. However, we will see that if we have a simple module which contains a weight element, that it should be a weight module. And of course, finite dimensional modules are finite dimensional over h, so they should contain a simple h submodule. What is not obvious is that all other finite dimensional modules are h-diagonalizable as well. So here, one has to use Weil's complete reducibility theorem, which states that all finite dimensional G modules are semi-simple. So category O contains all finite dimensional G modules. And as a negative example, the left regular U of G module, U of G, does not belong to category O. Of course, it is finitely generated, but it is not h-diagonalizable, and neither it is locally un plus finite. The action of UH and un plus on U of G is free by the Poincare-Berghoff theorem. So this is almost all for today. We complete this lecture with some questions for people who want to think about the content of the lecture. Question number 1, it is very interesting to think how category O changes if you substitute conditions 2 and 3 by the common condition that the universal enveloping algebra of the Borel subalgebra acts locally finitely. Question number 2, it is also very interesting to think what happens if we change the content of conditions 2 and 3. If we require that U of H acts locally finitely, while n plus acts diagonalizably. Question 3. It's an interesting question to think about what happens to Schur's lemma if we will work over the algebraic closure of Q instead of C. So the current proof manifestly doesn't work because C is an uncountable set while the algebraic closure of Q is countable, so the argument of the present proof doesn't work. Question number 4, what can one say about finite dimensional AN modules? So there is a very big difference between simple finite dimensional or finite dimensional modules over the Lie algebra and finite dimensional modules over the Weil algebra. It's interesting to think about this. And also a natural question, is it possible to define some analog of O for the nth Weil algebra AN? What kind of conditions, how can one adjust the conditions from the Lie algebra setup to the setup of the Weil algebra? Thank you very much. See you next time.